of a falling object. The purpose is very simple to observe a free fall motion. We're going to drop a ball, and that's going to be all. Computational model, brief explanation. We're going to use Newton's second law again, momentum principle, with drag force and gravity. Here is a quick video, what I did in this experiment. And here is the result, which is not really satisfying. 55% error. It is what it is. I just did it. Details of computational model. I've used those two formulas to measure the gravity and the drag force. For the drag force, that is kind of complicated, but law, C, A, those are all constants. So I just got the spec of my object and just applied it to it. The gravity is, you guys already know it, mg. Where g is 9.8 meters per second square. System sensor on things. I only I have my object as a baseball and a table right there. I'm gonna drop it on the table, from the table, and airs, the gravitational force, those are all my system. And that's what typically we actually see in the real world. So there will be no such huge distinction between those two. Procedure, very simple. Just drop it. Just drop the ball. Initial condition, here's where I got all my constant values. Get the radius of my ball, so I can get cross-sectional area of it and mass of it. I already measured the mass of it, and drag coefficient of a sphere is 0.47, so I just applied it. And the air's density, 1.2 kilograms per meters cubed. Those are all typical, all trivial, so it doesn't really matter. The height of the desk was 76 centimeters, by the way. Here's the observation that I got in my experiment. Looks pretty good, but the scalar value of acceleration was not so good, which is 4.4, around 4.4 based on the screen. Yeah. Here are a snippet of codes. A visualization, you guys already know what that is. Initial conditions, I literally just put all those values that I just showed you in this snippet of code. The third one is a bunch of Newton's second law of stuff. Get the force, get the net force, and get the acceleration. Using the acceleration, update everything. And especially for drag force, update it based on the current velocity amount. Here is the what you can get on the execution of that code. Drag force is not applied. As you can see on the screen, D is set to 0. So there is only one arrow, orange colored arrow that represents a gravity. Here, you can see a slight difference. There is a sky blue colored arrow that represents a drag force. Similarities and differences of those three. Here's what I actually got in this experiment. The acceleration was negative 4.4 meters per second square. I have no idea why I got it. I was supposed to get around 9.8, but yeah. Here is what I got for gravity only model. Here is the model that considered drag force. Still 9.7, which is still around 9.8. You say the experiment was kind of failed because the distance that I've used in this experiment was too short. Like in this in tracker, I have to manually click every single points of the ball, the movement of the ball. We should have a equilibrium state. But if there is no drag force, there will be only one force, which means we cannot cancel it out. So obviously, drag force is needed. So third model will be the right model that can have terminal velocity. What if? What if we throw it? Like, if it has more velocity, so it has more drag force. Well, in this case, you have more drag force means your object will be slowed down. You actually slow down the object means you're gonna have less drag force as time goes by, and eventually you will get to the net force 0 again. Here is the proof that I got in my model. The case drag is less than velocity, which is the case from at releasing it from at rest. And here's the next case. When you have more initial velocity, but as you can see, the direction is opposite, right? But we are eventually going back to the equilibrium, like the terminal velocity, which is around 39.3 meters per second. Precision, that was pretty good. They looked very similar, but the accuracy was not so good.